So this is more about preserving natural sinks of CO2 in the ocean, not so much geoengineering to enhance artificially the CO2 uptake, but this is still a very critical part. We talked, to open this series, we talked about the biological carbon pump. So obviously this is about restoring natural biological carbon pumps in the ocean. There are many co-benefits, of course. We can start anywhere. Let's say start here. Restoration permits CO2 uptake into new biomass, so you can have ecotourism and other fishing activities, others going on, where you have already degraded the habitats in many ways. So you have sediments with newer and older biomass that has fallen to the floor, let's say. So you have habitat restoration, which is going to create epiphytes and subaquatic vegetation. So mangrove-like things have roots in the water, brackish water, but they stick out of the water to do photosynthesis. They have special abilities to take salt water and exude salt from their trunks and so on and so forth. So they have evolved to live in salty waters, and of course you have salt marshes which are spread throughout the world, but more in the mid latitudes and so on. So habitat destruction releases carbon dioxide back to the atmosphere, so we have degraded the habitats pretty much everywhere. Restoration, of course, permits it back, as we said, and carbon sequestered underground. There is older carbon and newer carbon falling on top, and the main thing you want to do is increase the residence time of these things by minimizing perturbations. And as you read everywhere, coastal population keeps increasing, and I think 50% lives within 50 miles, and this number is going to keep growing as global warming happens, despite the threat of storms, sea level rise, groundwater salt intrusion, and so on and so forth. Storms, of course. Photosynthesis transforms carbon dioxide into plant biomass, as we know. There's a cute little egret or some nice bird sitting there, lots of fish, and you have seagrass meadow, mangrove forest, kelp, and carbon storage in large marine organisms. Elsewhere, I have also discussed the ecosystem services provided by whales and or elephants on land, for example, where they help with carbon sequestration, ion fertilization, and ecosystem pruning, and so on and so forth. So they have co-evolved to benefit each other. So it's a coexistence of some sort. Even though estimates of exactly how much whales contribute and so on remain kind of open questions, let's say. Okay, so respiration releases CO2 and other greenhouse gases such as methane and nitrous oxide. As you remember, methane is about 25% as powerful as CO2 in terms of greenhouse effects, and N2O is about 200 times. And you have to also worry about residence time. CO2, of course, stays for centuries in the atmosphere. Methane only has about a decade's life residence time. It's easily oxidized, and nitrous oxide can remain for a couple of centuries. So there are adaptive benefits in terms of ecosystems that protect us from erosion. They reduce flooding from sea level rise, and they are buffers against storms. They are filters for nutrients that are running off from land into the ocean, and they provide oxygen, increase oxygen, provide habitats for lots of fish, and of course they provide livelihood for those who live in, like Sundarbans and so on, are very, very rich in terms of providing livelihoods for fishermen and so on. Okay, so let's come back. I think this is the last one. Conclude deep sea storage, which is basically more about storing it in the ocean rather than active enhanced CO2 removal. Okay, nice topics, nice infographics. Thank you, Manu and others, and we'll conclude with the next podcast.